Module 2, Lesson 3. Module 2, Lesson 3 covers iterative techniques which involve in systems of linear equations. So naturally, I'll be introducing you to systems of linear equations, different iterative methods, the Gauss-Seidel method, its iterative formula, the substitution process involved in this method, and we'll try to evaluate a sample problem using this given particular technique. As we know, linear equation comes in two given particular forms. One is called the standard equation form, whereby your equations are often written like this, and respectively, the number of equations is equivalent to the number of unknown variables present on your given equation. Like in this case, they are often depicted by your variable x, x1, x2, and x3. We could also write down our system of linear equation in matrix form, which appears like this, whereby matrix A comprises of the coefficients of our given system of linear equation, which is a 3 by 3 matrix. Your matrix X, comprising of your unknown variables, which are x1, x2, x3, which is a 3 by 1 matrix, and your constant matrix C, comprising of the values C1, C2, and C3, which is again a 3 by 1 matrix. There are several ways to iteratively solve for this given particular system of linear equation, one of which is called the Gauss-Seidel method. This particular iterative technique is very similar to your Gauss-Jacobi method in a manner that the first few steps of your Gauss-Jacobi are exactly the same as your Gauss-Seidel method. In fact, the process differs only in the introduction of new values in the succeeding iteration, which involves in your substitution process. This particular technique forcefully accelerates convergence of your unknown variables by simply introducing new computed values over to your next or new computed variable. In this manner, this particular variable eventually converges faster, thus introducing your new value onto that same iterative process rather than substituting it onto the next iteration like your Gauss-Jacobi method do. Thereby, this particular process improves the set of computed values for your next iteration. If you notice, the steps on your Gauss-Seidel is very similar to your Gauss-Jacobi. Step 1, much like your Gauss-Jacobi, rearranges the order of your equation in a manner that the dominant coefficient for each unknown variable lie in the main diagonal of the system of linear equation. Your step 2, again, much like your Gauss-Jacobi method, obtains its iterative formula for each unknown variable by transposing the dominant variable on one side of the equation and dividing the equation by its dominant coefficient. However, on step 3, where iteration is evaluated, the process eventually begins the iteration by substituting initial values of zeros only for the first variable. After solving for the first variable, it is then substituted onto the next iterative variable in order to obtain its new values. The process is repeated until the substituting variables on the next iteration satisfies the terminating condition. Since all variables are again included within a given linear equation, then it implies that all variables must again satisfy the terminating condition, otherwise the iteration continues. The substitution process for your Gauss-Jacobi is actually illustrated by this given particular graphical depiction, whereby on your first iteration, you solve for the first variable, x1, applying the initial assumptions that x2 and x3 are zeros. After solving for the new value of x1, this new value of x1 is now introduced to your next computed variable, which is x2. On x2, notice that you require variables for x1 and x3. However, since there are no new values of your x3, x3 here remains 0 for your first iteration, while x1 now is introduced and is taken from your iterative solution for your x1. After solving then x2, you substitute the calculated x1 and x2 to your next iterative variable, which in this case is x3. And then the process goes on, all carried over to the next iteration until the terminating condition is satisfied. Let's try to apply it then on this given system of linear equation. We evaluated this particular system of linear equation last time using the Gauss-Jacobi method. Let's try to solve it this time now using the Gauss-Seidel method. So step 1 requires us to rearrange the order of equation in a manner that the dominant coefficient for each unknown variable lie in the main diagonal of their system of linear equation. Hence, our given equation like this is then rearranged into this given system of linear equation, whereby you would notice that the dominant coefficient for each unknown variable are now lying on the main diagonal of our system of linear equation, which are the ones that are highlighted in red. The next step requires us to obtain the iterative formula for each unknown variable. And much like our Gauss-Jacobi, we then simply transpose our dominant coefficient on one side of the equation and divide the equation by its dominant coefficient. So from our equation 1, we simply derive the iterative formula for x1, since x1 there is dominant, by transposing x1 and dividing the equation by its dominant coefficient 6, thus giving us an iterative formula for your x1 to be, again, much like your Gauss-Jacobi, to be equal to 11 plus 2x2 minus x3 all over 6. And from your equation 2, whereby x2 is dominant, we evaluate the iterative formula for variable x2, transposing then 7x2 to the other side and dividing the equation by its coefficient ends up with this given iterative formula for your x2 to be 5 plus 2x1 minus 2x3 all over 7. And from your equation 3, whereby x3 is dominant, we then simply transpose your dominant variable 5x3 to the other side of your equation and divide everything by its dominant coefficient 5, thus giving us our iterative formula for x3 to be 1 plus x1 plus 2x2 all over 5. We then begin the iterative process by substituting values of zeros in order to evaluate for the first variable, which is in this case x1. Thus, on our first iteration, I only substitute x2, which is equal to 0, as well as x3 equal to 0 on your variable x1, thus giving us an iterative solution like this with a value of x1 to be 1.8333. We then substitute and introduce this value of x1 to your iterative variable x2, thus giving us an iterative variable x2 solution to be like this. Since your previous x3 remains 0, you'd end up with this solution with a value of 1.2381. And then substituting your x1 and your x2 calculated value to your x3 iterative solution would have a value of 1.0619. We then repeat the process for the second iteration, substituting the last two calculated values, which were x2 and x3. Substituting them for your new computed x1 gives us a solution like this, with a new x1 equal to 2.0691. And again, we introduce this calculated x1 and the previous calculated x3 to your next iterative variable x2, giving us this solution with a new x2 value of 1.0021. And then we introduce on your x3 this previously calculated x1 and x2, thus giving us a new x3 iterative solution to be like this, with a value of 1.0147. We then check whether we could terminate the process by comparing the previous values of your x1, x2, and x3 onto this new value of x1, x2, and x3. And as seen from our previous solution, it is very noticeable that we simply need to repeat the process. Therefore, we substitute the last computed value of x2 and x3 onto your next iterative variable x1, which is found on your third iteration, which should give us a new x1 solution to be like this, with a value of 1.9983, from which we substitute this new x1 and the previous x3 to be 1.0147 to your next iterative variable x2, giving you a solution like this with a new x2 value of 0.9953. We then introduce this new x1 and new x2 to your iterative solution for x3, thus giving us a solution like this, with a value now of a new x3 equal to 0.9978. And upon comparing these calculated values to your previous second iteration values, we eventually see that we need to repeat the process again. Thus, on the fourth iteration, we substitute the previously two computed values x2 and x3 to your iterative x1, thus giving us a solution like this with a new value of 1.9988. And then we introduce this new value of x1 and the previous value of x3 to be 0.9978 to your new iterative x2 solution, with a value now equal to 1.0003. And then we introduce this new value of x1 and this new value of x2 to your iterative x3, giving us a solution like this with a value now equal to 0.9999. And upon checking the error on our previous variables of x1, x2, and x3, when compared to your new values of your variables x1, x2, and x3, we found out that we still need to repeat the process. Thus, we substitute the last two computed values of our variables from the fourth iteration to the first variable on our fifth iteration, thus giving us a new x1 solution to be equivalent to this with a value of 2.0001. And then we introduce this new value of x1 and the previous value of x3 of 0.9999 to your iterative x2, giving us a solution like this with an x2 value of 1.0001. And then we simply introduce this new x1 and this new x2 to your iterative x3, thus giving us a solution like this with a new value equal to 1.0001. And upon checking your previous values on the fourth iteration, we've noticed that we still need to repeat the process. Thus, on our sixth iteration, we simply substitute these previous computed values of x2 and x3 to your new calculated x1, thus giving us a solution like this with a new value of x1 to be 2. We then introduce this new value of x1 of 2 and the previous value of x3 to be 1.0001 to your next iterative variable x2, which eventually ends up with this respective solution and an x2 value equal to 1. We then introduce that previously computed x2 and x1 to your next iterative variable x3, thus giving us a solution like this with a final value of x3 to be 1. Note that at this point, the terminating condition is already satisfied, showing us that your Gauss-Seidel solution converges faster than your Gauss-Jacobi method, which eventually just substitutes new iterative values onto your next iterative variable. Thus, this substitution process eventually improved our iterative solution and ends up with only around 6 iterations as compared to the previous 11 iterations of your Gauss-Jacobi. Much like your Gauss-Jacobi, you could simplify the solution by summarizing a tabulated result for your Gauss-Seidel to look like this. Note that all computed values on this particular solution are simply rounded off to 4 decimal place since the terminating condition has a 4 decimal place value. This ends the module.